Good morning, everybody. My name is Martina. I am a PhD student in physical methods applied to biological anthropology at Sapienza University. Today, I will present a multi-parametric study carried out on archaeological human bones in magnetic resonance and X-ray imaging. The analysis of skeletal anatomy enables the identification of fundamental moments in their biological history, which have left a mark on bone, such as acute or infectious disease. Human bone is a composite material of a porous nature characterized by a complex architecture, which can be divided into a macrostructure and a microstructure. However, certain pathological conditions, the taphonomic and the hygienic phenomena, can alter the normal porosity of skeletal tissue, making the bone structure characterization challenging. One of the most common pathological conditions in archaeological skeletal remains is proliferative periosteal reactions or periostitis. Periostitis is a skeletal lesion associated with an inflammation of the periosteum, observable mainly on long bones, that occurs with the formation of new woven fiber bones with a highly pod-like appearance due to hypervascularization of pathological tissue area. Although periostitis can be identified by macroscopical analysis, diagnosis based on simple observation of dry bones does not consider internal structures. The aim of this study is to test the potential of high-field nuclear magnetic resonance microimaging to assess the porosity and pore size distribution in cortical bone on a sample of 2 archaeological tibiae from the Roman necropolis of San Donato in Urbino, in Italy. The results were compared with X-ray computed microtomography data obtained with synchrotron radiation on the same specimen to verify the efficiency of investigational protocol. A Bukreeva spectrometer operating at high magnetic field was used. Both samples were put into a NMR glass tube filled with the ionized water. Sequences at various echo times and diffusion gradient strengths were performed to define resection times in each cortical bone slice, to perform diffusion experiments and to obtain diffusion time behavior. Also, member diameters were estimated using combined diffusion times and relaxation times. In the first equation, we can see the relaxation times T2 of fluid in a pore in each slice that is proportional to its surface to volume ratio. Then the surface relaxivity Q and the surface volume ratio were estimated using the relaxation in the second equation of the diffusion times TT, obtained from measurements at short diffusion times. Assuming that bone canals are cylindrical, the mean pair diameters can be estimated with specific constant values. Also, we can use an X-ray propagation-based phase contrasting, data preprocessing and tomographic reconstruction of 3D volumes were performed using the Filterback project algorithm. XPCT images and segmentation were performed using imaging software and MATLAB. Before extracting qualitative and quantitative information, images were processed to eliminate artifacts due to experimental conditions. Volumes were venerized by applying an intensity threshold. Porosity was then estimated as the ratio of the volume occupied by voids within the sample of the total volume of the sample, taken as if was total full. So microimaging MRI acquisitions for the two samples are shown here. Mean per diameters are extrapolated from relaxation time measurements calculated from a region of interest, ROE, identified in slides. Diameters agreed with those estimated with X-ray images. Phase contrast X-ray images are shown here. A difference in tissue can be seen between healthy and pathological samples. The graphs shows the distribution of the number of pores related to their diameter. The pore diameters remains uniform in both samples. Porosity is derived from the ratio of the empty volume to the total volume of the sample as seen in the equation. The pathological samples has more porosity than the healthy one. A simple visual comparison between MRI and XPCT acquisition is shown here. In opposite to X-ray, in RMN images, the denser materials is darker. So in conclusion, there are too many conclusions for this study. The first one is the porosity index increased with the distance from periosteum in XPCT images, probably due to inflammation of the tissue caused by the periostitics. This shown that periostitic lesions in the internal structure of the bone can be evidenced with this method. The second one is that the mean per diameters in each MRI slice extrapolate to relaxation times and diffusion measurements agreed with the diameters estimated from XPCT images, demonstrated that micro MRI approach can be a valuable support for bioarchaeological research. So thank you for your attention.